very much, okay, got it. Very much enjoyed attending these talks the last few months, so thank you for organizing. Okay. What I'd like to talk about this morning is first give a short history of ice sheets and coupled ice sheets in CISM, the Community Earth System Model. And then I'm going to talk about some CISM and Community Ice Sheet Model, or CISM simulations that were done for ISMIP6, the Ice Sheet Model Intercomparison Project for CISM6 in the last couple of years. Then I'll briefly talk about a number of current projects that people are working on who are involved in the CISM Land Ice Working Group. And then I'll finish by talking about some of our plans and challenges ahead. And at the beginning, I wanted to acknowledge many people because this is started as a small effort, but has grown into quite a large effort. We have several people at NCAR in the Climate and Global Dynamics Division who are focused on ice sheets or who have helped us very much with software and coupling, including Gunter Legee, who's the scientific liaison for the Land Ice Working Group, and others who work with software engineering and ocean modeling. The CISM Land Ice Working Group has become quite an international organization with active members on 3 continents. And the people I've listed are people whose work I've cited in some way in the talk I'm about to give. As Craig mentioned, I've been active in ISMIP6, and some of the work that I'm talking about is a result of very substantial efforts by Sophie Nowicki, Heiko Gelser, Aylin Sarusi, and other members of the steering committee. The Community Ice Sheet Model has a long history going back to the Glimmer model, originally developed in the UK. And so there's several people who were fundamental in early stages of model development. Also, no effort like this succeeds without strong support from management. So I've been grateful through the years for support from the CISM chief scientists and from climate management at NCAR, and of course for programmatic funding, which was originally provided by the DOE Office of Science and in recent years has been provided primarily by the National Science Foundation. So I'd say that the kind of watershed event for coupled ice sheet modeling was the 4th assessment report, which famously said there was no best estimate or upper bound for sea level rise because ice sheets weren't treated well or at all in climate models. This led to expanded ice sheet modeling efforts in many places, and in particular in the CISM community, led to the formation of a land ice working group, and also led to the Department of Energy project called Icicles, which was focused on ice sheet model development, and led to early versions of CISM and also the bicycles model, which you may be familiar with. Then the first release of CISM, which was a successor to CCSM, the Community Climate System Model, was in 2010. And for that model, we had a very simple implementation of dynamic ice sheets, which I'll say a bit more about later, which were subsequently published around the time of AR5. And then in 2014, we had the first release of CISM with a higher order dynamical core, followed a few years later by an improved version 2.1. In the meantime, the Department of Energy and National Science Foundation, which had collaborated for some time on CISM, DOE decided to develop their own model, E3SM, and NCAR, as a result, made the decision to hire some additional people to work on land ice, sea ice, and ocean modeling at NCAR. And as a result of that, I was hired at NCAR in 2017. The next year, CESM2 was released. That's the current version of the model, but it keeps being iterated, 2.1, 2.2. And that's the model I'll mostly be talking about today. So simulations done as part of CMIP, and then some work that's going to be leading toward, we hope, CESM3 in a few years. So the first edition of CISM1, we used the Glimmer model, which was or what was called then Glimmer CISM, which had only a shallow ice serial dicore, and so not very accurate for the more interesting parts of ice sheets. But we also put a lot of work into a surface mass balance scheme for land ice, where the SMB was computed in the land model. And this is something that confuses people because people sometimes think that the ice sheet model computes everything, including its own SMB. But in fact, CLM, the land model, computes the SMB, and this has a lot of advantages, including that we don't have to develop two independent snow models. We take advantage of the very good snow model that CLM has. We get hourly coupling to the atmosphere as far as the SMB is concerned, and we get computational savings because we can compute on the land grid with multiple elevation classes and then use those elevation classes to downscale to the much finer ice sheet grid. So this is a wiring diagram. As I said, the coupling was one way. So the land model passed the ice sheet, a surface mass balance and temperature at different elevation classes, coupling going only one way. And the ice sheet model didn't pass anything back to the land model. We did publish some results with this. We had a pretty good surface mass balance for Greenland, and the plot here shows the SMB in Greenland increasing between the late 20th century, sorry, the ablation increasing between the late 20th century and the late 21st century with a pretty broad expansion of the ablation zones and a negative surface mass balance by 2100. We were a bit lucky here in that we had some canceling errors in the radiation budget that gave us a pretty good answer for surface mass balance, but we think that newer results don't depend as much on canceling errors, and we have a more reliable model generally. We did some initial experiments with forcing this, then the glimmer CISM model with the surface mass balance. And we were able to capture the broad Greenland flow, but as you'd expect from a shallow ice model, our ice sheets were pretty diffuse. And so this was a good first test, but we definitely wanted to improve the ice sheet model going forward. So our goals for CISM2 included a fully parallel higher order ice sheet model that would have some Stokes approximation that would be valid for the entire ice sheet. We wanted to have our land ice SMB calculations done in all simulations, not just a small number of custom simulations that were carried out by members of the Land Ice Working Group. We knew there were some issues with the snow physics, and for example, we had only a 1 meter firn layer. We wanted to improve that. And of course, also we wanted to support two-way coupling because that's the point of doing this in a couple model. And we were able, for the most part, to achieve those goals. As far as the ice sheet dynamical core goes, some of you may be very familiar with this, but for those who aren't, I'll just give a brief overview. The Stokes equations are the full three-dimensional equations that are typically cited as the gold standard or the accurate dynamic equations for ice sheets, where you solve for all three components of velocity and for pressure. But these equations are very expensive and difficult to solve for. So people usually do some sort of approximation. At the bottom end, people usually use the shallow ice approximation, which is valid in the interior of an ice shelf where there's ice sheet, where there's not much sliding, or the shallow shelf approximation, which is valid for ice shelves or for fast sliding ice streams. And then in between, you have these approximations, which are less accurate than Stokes, but more accurate than either shallow ice or shallow shelf. Bladder-Patin is very well known. And now there's various depth integrated approximations, which are nearly as accurate as Bladder-Patin, but much more efficient to solve. And that's what we've settled on for most of our production runs. So in 2014, we released CISM2, which was the first version of CISM that had higher order velocity solvers and also various new test cases and documentation. And then Bill Sachs, who's done a lot of software engineering at CISM, brought that model to the CISM framework. And then a few years later, we released version 2.1. That was the first version where we really supported Greenland in a robust way, where we could say, you can run this for Greenland and it's not going to crash, and you'll get a reasonably accurate, well-tuned result. And we also included the solver, depth integrated solver called DIVA, which is based on a very nice paper by Dan Goldberg from 2011, which, as I said, has some really nice numerical properties and accuracy and is also very efficient. So in CISM 2.1 also has all the hooks needed to connect interactively to CESM. It does a pretty good job with velocities in Greenland. This shows observed versus simulated ice speeds at the surface, and you can see there's a pretty good match. And this is an open source code, which anybody can check out from the ESComp repo, which is a repository where most components of CISM live now. So we did some analysis of the strengths and weaknesses of CISM 2.1, mainly for Greenland. And we found that there were some pretty significant thickness biases of the order of 200-300 meters in places. We have a hard time producing the Northeast Greenland ice stream, which is common in ice sheet models. And so the ice is too thick here, and then it's too thin in some other regions as a result of some combination of basal sliding at the wrong speed, or possibly the surface mass balance that we're using is not as accurate as it could be. The basal state we were pretty happy with. On the left here is a synthesis of Greenland's basal thermal state, where the areas that are blue are frozen and red are thawed, and gray is somewhere in between. And then with a similar color scale, this is what we get from CISM with Greenland. So you can see there's a good match, although to some extent these are not independent, because models did contribute to making the plot in the McGregor paper. And then moving on to ice sheets in CESM2. As I said, CESM2 supports interactive coupling with Greenland, but you don't always get interactive coupling with Greenland. That's something you can choose. So by default, most people who run CESM are not interested in interactive ice sheets. And so the ice sheet model CISM is set not to evolve. Ice sheets are fixed, but you do compute the SMB for ice sheets along the way as you run the model. So you can save that output and use it to apply to an ice sheet model offline later on. You can also allow CISM to evolve with one-way coupling, where you fix the elevation in the land surface in the land model, or you can do two-way coupling. And in that case, the ice extent and elevation, as the ice sheet evolves dynamically, are passed back to CLM. And the biggest challenge in doing this was that CLM has land units of different kinds, including glaciated and vegetated and crop and urban and so on. And with variable ice sheets, you have to allow bits of the land to go back and forth between glacier and vegetated, and you have to conserve heat and water and things along the way. And that took quite a bit of work, but once that was done, we were able to do full two-way coupling. We also have improved snow physics, which are described in a paper by Leo van Kampenhout from a few years ago. So this is just a new version of the plumbing diagram I showed a few minutes ago. We now have more arrows that are related to ice sheets. We have two-way coupling, as I said, between the land and the atmosphere. We have runoff fluxes. For example, both the land surface can produce liquid runoff, and the ice sheet can produce calving runoff or liquid runoff from the base of the ice sheet. Those are given to the coupler and then passed on to the ocean. Also, it turns out to be trickier to update atmospheric topography than land surface topography. But periodically, we can take the new topography in an evolving ice sheet, and we can feed it to the atmosphere offline, and then restart the simulation with a new atmosphere. One of our new atmospheric land interface. And one of our goals is to be able to do this at runtime rather than having to stop and restart the model. So that's a broad overview of what CESM2 can do with ice sheets. Now I'm going to talk about the ISMIP6 framework and some experiments that were done using CSM or CISM or the combination that contributed to ISMIP6. So as you may know, this ISMIP6 is the first CMIP project with an ice sheet focus, and its primary goal is to estimate past and future sea level contributions from ice sheets, with a secondary goal of investigating feedbacks due to coupling between ice sheets and climate models, which is in a less mature state as of yet. And there were generally three kinds of experiments that fall under the ISMIP6 umbrella. There's your CMIP6 model run without dynamic ice sheets, but producing lots of results that are relevant for ice sheets. And then you have standalone ice sheet experiments, which are focused on sea level projections, and then coupled climate ice sheet experiments to explore ice sheet impacts on the climate and feedbacks. And we were involved in all three kinds of experiments. So I'll start with the first kind, which is just some ice sheet relevant results from CESM. If we look at the Greenland surface mass balance in a pre-industrial or mid to late 20th century configuration, it's pretty good. This compares the Greenland SMB from the Rackmo Regional Climate Model to CISM2. And you can see that CISM2 does a really nice job of capturing ablation zones, even in where there's quite a bit of spatial detail. This is a result of having multiple elevation classes, so you can downscale with good spatial resolution, and also having a very good snow scheme and some work that went into the atmosphere model to improve the surface winds, and some work that went into the atmosphere model, the atmospheric physics, that really help with the long wave cloud forcing. The main biases are two. In the southern interior, you'll see we have too much accumulation in southern Greenland in CSM, and that's largely a question of resolution. Rackmo concentrates the precipitation near the southeast coast, and CSM lets it come into the interior. We also have a bit too much accumulation, too large an area with a positive SMB in the north, and those have been both longstanding biases now. As you might expect, when you warm the climate, the ablation zone expands, and that's illustrated here. This is from an experiment where you increase CO2. Well, you can do this in one of two ways. You can increase CO2 by 1% a year in a transient sense out to year 140 or 150, at which point it's quadrupled, or you can just quadruple it instantly. And these are some experiments looking at what happens in both kind of experiments. And one thing that's interesting is with the abrupt 4 times CO2, the ablation area increases quickly, and then you can see it's way up here by nearly half the ice sheet by year 150. With 1% CO2, it takes quite a while for things to get going, and by year 150, you're not caught up with the 4 times CO2 in terms of ablation extent. So this is a suggestion that since the real world, of course, is a transient experiment, that what we see now or what we'll see in the near future may not reflect what's going to happen in the longer run when things equilibrate. Interesting paper by Brice Noel et al. That came out recently looked at thresholds for Greenland warming. When you have a surface mass balance that's negative for Greenland as a whole, then it doesn't matter if calving goes to 0, the ice sheet will shrink. And this study determined that happens when you get global mean warming of about 2.7 degrees Celsius, which is about 4.5 on average over Greenland because of Arctic amplification. And in a high emission scenario, SSP 585, this is reached in the 2050s, but not reached at all in the 2.6 scenario. So in this case, there's a very big difference between what happens between the high and low emission scenarios, as you might expect. Looking at Antarctica, this is a slide from Devin Dunmeyer, a student working with Jan Leenaerts, who's done a lot of work on surface mass balance in CESM. In this plot, the lower curve is from CSM1, which was our CISM5 model version, and then the upper one is from CESM2. And these are some various reconstructions and results from other models. And as you can see, the SMB has gone up quite a lot. In Antarctica, in a modern climate, there's very little melting, so the SMB is dominated by snowfall. So it snows too much in CSM2. You can see that the spatial patterns generally are pretty good. Here's CSM2 and here's the reconstruction. But if you look at a different spot, you can see that we're getting too much snowfall, especially along this coast. And that's something that we would, of course, a bias we'd like to reduce. You can also see an upward trend since 1950. Now I'm going to move on and talk about some coupled experiments. Just as a reminder, the coupling consists of a surface mass balance in the land model that's fed to the ice sheet. We're adjusting the ice sheet topography periodically, and we're sending freshwater fluxes to the ocean. And the experiments that we've done that you can now read the publications include a pre-industrial spin-up over 10,000 ice sheet years, and then a transient 4 times CO2 run, and historical followed by SSP 585 runs described by 2 papers led by Laura Muncheworth that were published last year. The spin-up is tricky because it takes about 10,000 years for an ice sheet to spin up, and you can't run a climate model for 10,000 years in a spin-up. And so the strategy chosen here, described in the paper by Marcus Livestrom et al., was to alternate between running with all the components active and then running with all components but the atmosphere active, with the atmosphere being the most expensive component. And since you're doing a lot of the spin up and you're accelerating the ice sheet while you're doing this, the so-called JG part of the spin up, the letters don't mean anything. That's just CISM ComSet jargon. But BG is fully coupled. JG is you're using a data atmosphere. And they achieved savings of about a factor of 2 compared to doing things without the JG step, and a factor of 20 compared to doing things with a synchronous ice sheet. And so in that way, they were able to spin up the ice sheet without having to spin up everything else at the same time. And the result is the ice sheet comes to pretty close to equilibrium with climate at the end of its spin up. The ice sheet is larger than observed, with a volume about 8% larger than observations. The residual mass trend is very small. Most of the excess volume is in the north because we have a positive surface mass balance there. And even if the positive SMB is not very big, over time you will build an ice sheet there. But we decided that it was better to have an ice sheet in equilibrium with the climate than an ice sheet that's a better fit to observations, but not in equilibrium. So this is what we use as a starting point for our ISMIP6 simulations. In the SSP585 simulation that started from, well, first the spin up, then a historical run, then SSP585. By 2100, you have a big increase in CO2 and global 2 meter temperature. The Atlantic meridional overturning circulation more or less collapses to about 8 sverdrups. And what's going on in Greenland during this time is you start off with the near balance in the mass balance for the ice sheet, and you're losing 1,000 gigatons per year, or close to 3 meters equivalent sea level rise by 2100. And by that time, you have about 100 millimeters or 10 centimeters of global sea level rise as a result of increased ablation in Greenland. This doesn't include potential ocean effects on Greenland that could lead to a larger contribution. And this is consistent with the ISMIP6 Greenland projections that were done by a number of groups and described in a paper by Heiko Gelser et al. In that paper, you have, under the 8.5 scenario, again, about something in the neighborhood of 100 millimeters of sea level rise, mainly from increased surface ablation in Greenland. And in the case of Greenland, there are some uncertainties, but by and large, the uncertainties are what we're used to seeing in climate models, and at least semi-quantitatively, there's good agreement across models. With Antarctica, the story is very different. The paper led by Elin Sarusi for ISMIP6 Antarctica showed that a wide range of results and competing effects, where you have more snowfall for the East Antarctic ice sheet primarily, but also in some cases considerable mass loss from the West Antarctic ice sheet, but that varies a lot across models. And this demonstrates that Antarctica continues to dominate uncertainty in sea level projections. And this was brought out further in the recent Nature publication by Tamsin Edwards and others, which summarized results from ISMIP6 as well as the Glacier MIP project. So I'll just describe one effort that came out in a paper in the cryosphere earlier this year, where we tried to use CISM to dig down a bit into the projections and the ocean uncertainties. And our hypothesis was that by 2100, the ocean may have warmed enough to drive major sea level change in Antarctica, even though not much of that sea level rise actually shows up in our model by 2100. Most of it shows up much later. So the idea was we spin up the model where we adjust basal friction parameters beneath grounded ice and basal melting parameters beneath ice shelves to nudge the ice thickness in the model toward observations. So we come up with a steady state ice sheet that's not too far from observations. And these plots here show the velocity, and you can see the observed velocity structure and the model velocity structure are very close, even though we don't tune specifically for velocity. We tune for thickness, but velocity comes along for free, as it were. And then following spin-ups, we did forward runs out to 2500, and we did multiple forward runs with different sub-ice shelf basal melting schemes, and ocean forcing from different ESMs that were with ocean forcing provided by the ISMIP6 project. And what we found is a big spread. We found that sea level rise by 2500 ranges from about 150 millimeters to about 1.5 meters or more, depending on the flavor of basal melt parameterization you choose. And ISMIP6 provided different flavors that were called, for example, Menant and Piggle. And you can vary the physics a bit. And ISMIP6 also provided different ocean models, and HADGM2 gives you the greatest ocean warming, and CISM2 gives you a more moderate amount of ocean warming. And so if you compare, for example, this panel to this panel, you can see in this panel some shelves are thinning, but not much else. And in this panel, you have massive retreat of the Filchner-Ronne and the Ross ice shelves over the course of a few centuries. I should mention that these simulations are done at 4-kilometer resolution, but results are pretty similar at 2 kilometers, which was the highest we got. Also, that these experiments include the marine ice sheet instability, MISI, but no hydrofracture or Mickey in these simulations. So things become unstable, but they don't become unstable in a very fast and dramatic way. It takes a few centuries to play out. You'll also see here that even in the more sensitive simulations, not much happens in the Amundsen Sea, which of course is where the most interesting things and the greatest mass loss is happening now. So we looked into that a bit and found out that the Amundsen sector, especially the Thwaites Basin, in our model has threshold behavior. And it depends on how you initialize the model and what basal friction law you use for the model. And under some assumptions, you get almost no retreat. And under other assumptions, which are, I would say, as defensible as assumptions that lead to this, you get this. You get collapse of the Thwaites sector, and you get an additional sea level rise of 1 meter or more, in addition to what I showed in the previous plot. So you can get close to 3 meters of sea level rise if you have certain basal friction laws and initial protocols. And the way this happens is interesting too. This plot on the upper right, the different colored lines show the grounding line location at different times, starting at 2100. And then at 2200, the grounding lines are treated, but it's hung up on this subsurface ridge here, which in some simulations, it doesn't get past that. But in other simulations, it hangs up there for a few decades, and then it gets past that ridge. And after that, there's nothing to hold it back, and collapse of the whole basin is pretty much inevitable because everything is so deep here, and MISI is very effective. So I will stop the ISMIP6 summary there and just summarize a few things I've learned from this effort over the years. When I started this more than 10 years ago, I was very naive about how much work was involved. And I put in a proposal for a project, a couple ice sheets in CSM. And it turned out to be much broader than a project. It's pretty much turned into my career. And it's a very interesting career, but it really is kind of a multi-decadal calling, if this is something you want to do, that involves a really large community. Absolutely critical to have in your community if you want to do this are good software engineers, dedicated software engineers, because when you put dynamic ice sheets and climate models, you break many, many assumptions that went into the earlier global climate models, and you have to make thousands and thousands of lines of code changes, which are sometimes very, very intricate. At the beginning, I thought that if we just went from shallow ice models to higher order models, we'd have the ice sheet models we needed. And we now have higher order ice sheet models, which are great. But there's a lot of physical processes that we don't understand very well, and particular basal sliding and iceberg calving, where in the runs I described just a few minutes ago, we tuned those a lot to agree with modern observations. But we'd really like to be able to let these things go and evolve physically. And that would enable us to do longer simulations, like on paleo timescales, without fixing things that we really shouldn't fix beyond timescales of a century or so. And of course, it's become a huge effort. And those of us at NCAR, our primary role is to develop models and support the community. And we love to do science ourselves, but there aren't nearly enough of us to do the nearly infinite number of simulations that one can do with a dynamic ice sheet model as you add capabilities. So we really love to see people join the community and come up with new simulations that we might never have thought of. And the larger and more diverse our community is, diverse in terms of age, gender, nationality, whatever you can think of, the more interesting science gets done in all different directions. And finally, ice sheet ocean coupling looked like a hard problem at the beginning, and it's still the hardest thing that's left, I think. Then I wanted to go briefly through a number of projects that are being done right now and at various stages of preparation or review. A few projects involving paleo ice sheets, long-term future of Greenland, and some new work involving mountain glaciers, and some new software engineering work that will allow us to run coupled to Antarctica. So starting with paleo simulations, Aaliyah Summers was a postdoc at NCAR, and she did Greenland simulations of the last interglacial, showing the ice sheet shrinking from 127 Ka to a little past 123 Ka, bottoming out at around 121 and then starting to regrow. And one of the interesting things about this simulation is that it matters a lot how you treat vegetation. If you use fixed vegetation, you don't see nearly this much retreat. If you periodically update the vegetation using the biome vegetation model, you get substantially more retreat, possibly even too much retreat. But this shows the importance of doing better with dynamic vegetation if we're going to model ice sheet retreat on paleo timescales. A little bit after the last interglacial, at about 116 Ka, we had ice sheet inception in the Northern Hemisphere. These are experiments that Marcus Lipscomb has done. And he finds generally ice sheets form without having to do any special tuning of the model, just the orbital and greenhouse parameters. Ice sheets form in the right places, like the high Canadian Arctic. And one thing he found is that it was hard to incept glaciers in Scandinavia until he had the idea of closing the Canadian Arctic archipelago gateways after 500 years. And that has the effect of rerouting some fresh water. And at that point, you start to see inception in Scandinavia. So in this way, you see how inception at some places enables inception at a later time in other places. And these are some simulations focused on the last glacial maximum by Sarah Bradley and Michaela Petrini, where they're running CISM simulations at 26 and 21,000 years ago, again, using the biome model to help them out with vegetation. And the idea is to use the resulting SMB to force CISM. And so that's what what they're working on. They're also working on getting ice streams to form in the North American ice sheet, which turns out to be pretty hard near the land boundary, but we've recently added some hydrology schemes and some geological information that seems to be helping. Then coming to the present and the future, these are some Greenland deglaciation simulations where basically you start with your 4 times CO2 scenario and you just extend it. And what one finds is that within about 3 centuries, you no longer have any ice on the coast, so you don't have any calving. Everything is driven by the SMB. And then with 4 times CO2, it takes about 1,700 years to deglaciate virtually the entire ice sheet. And it's mostly solar radiation albedo feedback after the 1st century. One interesting thing they found is that when the SMB reaches 0, that doesn't mean you're done, because the ice sheet still has the opportunity to retreat to areas where the SMB is positive. And you have to actually get to a little bit higher threshold than that before you drive total deglaciation. There's been some work recently in using variable resolution atmosphere grids in CSM with the hope that this can improve our precipitation over ice sheets among many other parts of the climate. And these are some promising simulations where you have your 1 degree CSM surface mass balance over Greenland that I showed earlier. And if you go to variable resolution with resolution focused over Greenland, you get a much sharper snowfall maximum over Southeast Greenland, which is in better agreement with the RACMA regional model. So we're now starting to develop Arctic grids and Greenland focused grids so that we can do better with SMB just by virtue of having better resolution in regions of where there's orographically forced precipitation. However, this doesn't help much with our northern Greenland bias, so that has a different source other than resolution. And then continuing, we're starting to develop variable resolution grids for different parts of the world. The continental United States is a target, and another target is high mountain Asia, where this is what we call the whale, because it sort of looks like the whale, a whale. This is the region over high mountain Asia where you have the Himalayas and the Karakoram and Hindu Kush, and it's resolved as fine as 7 kilometers. And then out here is 1 kilometer, and you have transitions in between. And the goal is to see if, with resolution like this, if we can actually resolve surface mass balance and orographic precipitation in high mountain regions such as the Himalayas. And this is a recent simulation. It may be a little hard to see with the color scale, but blue is where you were starting to accumulate snow in the Nepal Himalayas, and then red is where the surface mass balance is negative. And we're not fully spun up yet. So when it's fully spun up, I think we'll see a better balance between the accumulation regions and the ablation regions. One of the motivations for having a better surface mass balance over a region like high mountain Asia is then you can use that surface mass balance to force a glacier model. Now, people do this, of course, with regional models, but CSM with variable resolution is kind of like a regional model. It's just that the nesting is a little bit cleaner because it's all one atmosphere. And what we'd like to do is apply the surface mass balance that we get to glacier models. And a graduate student named Samar Minalah at the University of Michigan is about to start working on that with an eye toward understanding or projecting glacial lake outburst flooding. And as preparation for that, we've started applying CISM to mountain glaciers with a hopeful hypothesis that if you have an ice sheet model, you also have a glacier model. Now, that's not strictly true. Glaciers need a resolution down to maybe 50 to 100 meters. And so you need an ice sheet model that doesn't have an extremely restrictive time step as you reduce delta X. But our time step scales roughly linearly with delta X. And because glacier regions are smaller than ice sheet, it sort of balances out. So we can have about the same number of grid cells to study a mountain glacier region as we would use to study Antarctica at a much coarser resolution. And it's also nice if you have some kind of load balancing, so you're not applying lots of processors to areas that are free of glaciers. But anyway, we've just started on this, but one of my favorite parts of the world is the Bernese Alps. And so I thought we would start there. And this is just a result of a short simulation where we've simulated ice velocity in the Bernese Alps and the Aletsch Glacier, which is the longest glacier in the Alps. And it looks reasonable so far. So at least we know the model works there more or less out of the box so far. So that's encouraging and something we want to extend to high mountain Asia. Also, a big software effort of the last few months, led by Bill Sachs again and Mariana Berkenstein, is to add support for interactive Antarctic ice sheet coupling, and also for being able to run multiple ice sheets in one simulation, including paleo ice sheets. So once we have that capability, which is almost done on the software side, we can focus on the scientific side. And we're going to use POP and CISM coupled to study Antarctic evolution at the last interglacial and what that can teach us about the future. And also CSM, as you may know, has a new ocean model, MOM6, developed primarily at GFDL. MOM6 allows circulation beneath ice shelves. So we're very excited that we'll finally be able to actually have ocean circulate underneath an ice shelf instead of ending at the calving front. And we've done some idealized simulations along these lines, led by Gustavo Marquez for the MUSOMIP coupled ice ocean project, the first phase. We're also working on contributing to the GHub project, which is an NSF cyber infrastructure project focused on ice sheets, where our part of the project is to bring CSM data sets and diagnostic tools relevant to ice sheets and make those available to the community. Going forward, there's of course lots more work to do. One of the things I've been working on is a subglacial hydrology model, where it's not the most complex hydrology model. It's based on the very simple principle that if you have sources of melting and you make that water run downhill, you can compute what the steady state fluxes should be. And this is a plot of steady state fluxes for the Antarctic ice sheet after the model is spun up and generating basal melt in certain places. And it's certainly nice to look at, and it does seem to match pretty well with areas where we know there are ice streams and possibly basal water contributing to lubricating the bed. We're also looking at new friction laws, including a recent suggestion by Zoot and Iverson for a friction law. In many of our simulations, we prescribe the cat in front. We'd like to allow it to evolve freely. That turns out to be very hard to do, but we're working on that. And we have not yet, but would like to implement hydrofracture and cliff collapse parameterization so we can include those possible effects in our experiments as well. And the documentation has fallen behind, and we're wanting to get that updated in preparation for hopefully a new release, possibly CISM3 in the next couple of years. On the CISM side, we're working on a diagnostic package for land ice. We still have one big technical challenge, which is to allow the land ocean boundary to move back and forth as ice shelves advance and retreat, because we need that in order to have a surface mass balance over the ice shelves wherever the ice shelves need them. We have, as I mentioned, some surface mass balance biases for both ice sheets, generally excessive snowfall in certain regions that we would like to work on through higher grid resolution or other methods. We have a really big challenge in that the delivering heat to a subshelf cavity in an ocean model typically requires very high resolution in your ocean model, for example, 5 kilometers or less. And we can't do that at a global scale. So we're looking at different parameterizations. There are plume models, PICO is one that have been used by other modelers. And we have some other ideas we'd like to look at to more realistically translate changes in the large scale ocean circulation to heat delivery to subshelf cavities. And as Matt Hoffman talked about in a recent talk, we have aspirations to have a sea level model as well, where we include isostatic adjustment and changes in self-gravity of ice sheets. But at the moment, that's pretty far on the horizon. We don't have any definite plans to work on that in the next year or two. I'll just say at the end, I read a lot of papers that say, the conclusion says something to the effect of, we need coupled ice sheet and ocean models to further explore this question and reduce uncertainties. And I absolutely agree with those statements, and I think it's very important. A couple of recent indications. This is a figure that Sheena Sadai showed in a talk just a couple of weeks ago, showing that it makes a big difference to the global mean surface air temperature, whether you supply large freshwater flux from Antarctica at a certain time or not. And this is a very large freshwater flux. We'd like to look at a range of freshwater fluxes and see how much that affects things globally. Also, a recent paper looked at global mean sea level contributions with and without a high resolution ocean model in CISM. And what they found is that when they use a low resolution ocean model, they get a much higher sea level contribution than with a larger contribution than with the high resolution 1/10 degree ocean model. Now, how they compute sea level rise is pretty highly parameterized, but it does indicate the importance of resolving ocean eddies, which the 1 degree CMIP models are not able to do. So I'm hopeful that with this coupling, we'll be able to have better understanding of these feedbacks and possibly reduce uncertainty related to thresholds of stability for Antarctica. So for example, under the Paris Agreement, the goal is to limit warming to as close as possible to 1.5 degrees. If we were to exceed that and go to 2 degrees, would the West Antarctic ice sheet be unstable? Or do we have to go to 3 degrees before WACE is unstable? I think that would be, that's a really interesting question to explore that we can, couple models can contribute to. On the other hand, the recent AR6 report and its sea level predictions specifically says that there are deep uncertainties in ice sheet processes, including Mickey, that are very hard to quantify and give accurate rates, for example, to people who are interested in climate adaptation. And at this point, I don't see that coupling will do much to reduce that deep uncertainty. That has to come from somewhere else. So just to summarize, there have been a lot of recent advances in ice sheet coupling in CISM2 and CISM, and we hope to continue those moving forward toward the next release, CISM3. And many people in the Land Ice Working Group are doing some really interesting science with these new capabilities. And the coupling of ice sheets to the land and atmosphere is pretty mature now, and we're pretty happy with how that works, but still in the early stages with the ice sheet ocean coupling. And that uncertainties are sea level are large, and as you know, continue to be dominated by the Antarctic ice sheet. So just finally, I'll say that in the Land Ice Working Group, we have two co-chairs, Jan Lennertz and I, and we have two liaisons at NCAR who are dedicated to supporting the community, Gunter Legee and Kate Thayer-Calder. We meet twice a year, and since COVID started, we've also had monthly Zoom calls, and we absolutely welcome new participants if you'd like to learn about or contribute to anything I've described in the last 45 minutes. So I will stop there, and thank you for listening, and I would be glad to take any questions you have. And Craig, shall I stop sharing or leave that up?
Maybe it'd be nice to go back to your conclusion slide.
Sure.
Thanks ever so much. That was a fascinating talk. Do we have any questions from the group?
And I'm not able to see the chat in screen sharing mode. So Craig, if you could relay any questions in the chat, or also if verbal questions are great too.
Yeah, we don't have any questions in the chat as of yet. Oh, we've got Matthew has his hand up.
Yeah, I have a quick question. Thanks, Bill. This was super interesting to see the history of how CSM evolved over the past decade. My question is really about ice-ocean interactions, and you did talk a little bit about it. And I was wondering if the current model, I believe, does not do sub-ice shelf circulation.
POP does not do sub-ice shelf circulation. It
And
sees just a wall at the cabin front.
Right, and there was some talks at some point about switching ocean models and pick another one that would be maybe more, capable of doing this sort of things. Is there a timeline? Is this a priority?
Definitely a priority. The decision was made about 4 years ago. And one of the new hires a few years ago was Gustavo Marquez, who'd been a postdoc at GFDL, is now a project scientist at NCAR. And his main job has been to fully implement MOM6, test it, get it to be scientifically supported in CSM. So in the latest CSM release, I believe it's 2.2, MOM6 is functionally supported, meaning you can run the model with MOM6, but no guarantees that what you get will be scientifically accurate. But the hope will be that in another release 1 or 2 years down the road, we'll also be able to scientifically support MOM6. So that's definitely going forward, and we've had a really fruitful collaboration with the GFDL ocean modeling group.
Thanks, Bill.
I see Ron Miller has his hand up.
Yeah, hi. This is really impressive, just how much work you all have done. And I think one of the things you've been clear about along the way is that there are a lot of uncertainties in a lot of places where you are kind of taking first guesses at what the key physics is. So I'm just wondering, like, what kind of questions do you think you can ask of these models where you have some confidence in the answer, and what do you think are basically just kind of first guesses where there are a lot of unknowns that really make it tough to say anything definitive? I mean, can you distinguish between those two categories, or just give some examples?
Well, I think Mickey would count as kind of an unknown, or maybe a known unknown, where you have an ice sheet process, which depends on certain parameters that are very hard to constrain, and I don't know, I don't know how you constrain that as well as I would like to constrain it for sea level projections. I would say I'm hopeful that we can actually do a better job than we do now with melt rates beneath ice shelves. I think ISMIP6 was a good start, but as you may know, the process was basically to take thermal forcing anomalies in large-scale CISM ocean models and just extend them horizontally beneath ice shelves. And then you have a parameterization that converts a given amount of thermal forcing to a given melt rate. I think that by using either ocean models that are run at higher resolution, like Jeff Ridley talked about for UK ESM and Matt Hoffman with the variable resolution impasse ocean model, or by nesting a regional model. For example, MOM6, it's possible to nest within itself at a higher resolution. I think with higher resolution models, we can do a better job of actually resolving the circulation in ice shelf cavities. And even if we're not able to do that efficiently enough to run multi-century simulations, maybe we can at least learn enough from that to be able to parameterize it more accurately. So I guess that's an area where I think there's a lot of unknowns, but I am hopeful.
Thank you.
We have a question in the chat from Olga, and then I see someone has a hand up. Olga, would you like to unmute? Perhaps not. So she's asking, what determines the spin-up time for either ice sheet?
There's a couple of things. One is if we're nudging parameters, the nudging has an intrinsic time scale. And that's typically a few thousand years before things have settled. Also, they're spinning up the temperature field, where it takes something like 10 to 20,000 years to spin up the temperature field enough that the the viscosity settles down, and then you have the flow you're going to actually get. But there are ways to accelerate that a little bit. So ballpark, I'd say something like 10,000 years. And at 4 kilometer resolution, we can do that in, say, a day. And at 2 kilometer resolution, it takes a bit longer.
Thank you. I see, I think it's Yuin. I'm sorry, I might be pronouncing your name incorrectly.
No worries, it's Yuxing. So thank you for the great presentation. I just have a question about icebergs and how it's handled in the model. I think you mentioned a little bit. How are icebergs calved, and once they're released into the ocean, do they travel along with currents and wind? I know it's not very relevant to maybe like the modern simulations, but for paleo, it might be more relevant.
That's a great question. And so far, that's not something we do very realistically. The calving flux is typically sort of a time average steady state flux. So we don't simulate rifting in individual calving events in CISM, at least not so far. And then as far as CSM goes, when a solid ice flux goes to the ocean, you melt, you take the volume of ice that was delivered to the ocean in a certain time frame, like a year, for example, and then you determine how much energy is needed to melt that. And you spread that energy over a radius of typically, say, 300 kilometers. And then you apply that as a cooling flux over the course of the year. So everything is very smoothed out in time and space, and we don't have drifting icebergs. There has been some development work in the CISM model on allowing icebergs to drift around, but not yet in a version of the model that we run in CESM. I know the GFDL folks have a big interest in iceberg modeling, and we're hoping at some stage to collaborate with them to have a better representation of icebergs.
Great, thanks.
That's really interesting. I'd be intrigued to know the distribution of the iceberg melt and the depth range that you commit to the cooling.
I believe that's done. It's all done at the surface, at or near the surface, but over a pretty large spatial range. because if you do it over in one grid cell, you crash the model with negative salinities.
Yeah, I guess I suppose as they break up, the closeness of them to the surface is that's a fair assumption, perhaps.
But for a larger iceberg, maybe not.
Yes, but perhaps the majority of them the melt rate is perhaps higher when they're smaller.
Yeah,
it's interesting. And do we have any other questions from the group? I have a question that perhaps, but it's related to the ocean. You showed a study which I think is really interesting, where they looked at the response of the ice sheets to changing resolution.
Mm-hmm.
I was just wondering if you happen to know of any discussion going on around how one might improve this disagreement in the lower resolution models. For example, specific tuning to the mixing parameterizations on the Antarctic shelf, or something like this.
You're speaking about resolution in the ocean model?
Yes. Yeah.
Sorry. Yeah. So
Topic
so what are people trying to do? I think generally two approaches. You can bite the computational bullet and run at higher resolution, either globally or regionally. If you have a model that can be regionally refined, or you run your regional models at high resolution and try to learn stuff and develop intuition, and then turn that into parameterizations.
I was just wondering if you might have sort of a favorite specific parameterization for eddies on
do I have a favorite eddy parameterization? No, not really. I have had some interesting talks with Adrian Jenkins about how one could model the subshelf circulation with a reduced order ocean model, where you a model that is simplified enough that you can run it at very high resolution, like 1 kilometer, and at least get the broad features of the circulation. So I would be interested in developing and implementing such a model, but there's still the challenge of how that links to the eddy transport up onto the continental shelf.
Yeah, that sounds really interesting. It's super tricky, particularly when you're constrained by the numerics of the problem.
Yep.
Do we have any further questions? Everyone just saying thank you and fascinating talk and such things in the chat.
Oh, thank you.
Okie doke. We should probably, we're ever so slightly over time here, so we should probably close off and let people get on with their next meetings and things. Thank you ever so much, Bill, for giving us a talk this morning. I'm really looking forward to putting it up.
My pleasure. Thanks for listening.
Okie doke. Thanks, everyone. Cheers. Bye for now.